All right, chapter 3, section 4, graphing what's called vertex form of a quadratic equation. All right, this one definitely looks a lot messier than some of the other sections that we've done so far. All right, the real signature look for a vertex form has to do with this parentheses squared. Okay, and because it's a parentheses squared, this is actually where we get the x squared. You'll notice that there's an x on the inside and then the squared version right there. Okay, that's going to give it the parabolic shape, that U shape ultimately when I graph it, because it's going to end up with an x squared. Essentially, this is just a rearrangement of what we've done in the previous 3 sections. So just to remind you where we've been in the previous 3 sections, in section 1, we dealt with just ax squared. In section 2, we added in the c, so it was ax squared plus c. And then in section 3, we saw the fully fledged polynomial form, ax squared plus bx plus c. All of those are essentially what we just call a polynomial, the stuff that we dealt with in chapter 2. And it's also called standard form. Standard form polynomials are just like this sentence form. This is a rearrangement of that in this section. If I were to take this parentheses squared and actually square it, so in other words, I would take the x minus h and multiply it by itself, x minus h, distribute, collect like terms like we did in chapter 2, and then add in this k value at the very end, what I would end up with would look a lot like something in sections 1 through 3. I would have a polynomial. All right, and it would have an x squared highest degree. And that's why it's going to end up having that U shape. But there's a reason why this form right here is super valuable. This form is called vertex form. And as the name suggests, it provides us with the actual location of the vertex. Now, why is that so important? Where do we see this in other aspects of math? Kind of important to understand is that you've dealt with stuff like this before, a rearrangement of an equation. When it came to linear equations, the equation form that you're probably most familiar with, y equals mx plus b, is simply a rearrangement of a standard form of a line. The standard form of a line, in case you didn't know, was ax plus by equals c. Okay, and that's something that we typically didn't deal with when it came to graphing lines because there wasn't a lot of information. It would take a lot of work to get the stuff necessary out of that equation, as opposed to y equals mx plus b, where there was a y-intercept that was shown in the equation and a slope. Basically, just looking at the equation, I could graph what I needed. And so we use that form more often, even though it's a rearrangement of the original. This is the equivalent of that comparison when it comes to quadratics. We'll be able to pull out the most information from this form. And when we get into section 5, there's going to be another arrangement of a polynomial that we'll be able to see where, again, we get a lot of information, if not as much as this. Okay, this will end up being the fastest way to graph a quadratic based on this vertex form. And here's ultimately why. Anytime we are, again, asked to graph a function, we're going to need an XY table to do it. I mean, I guess the exception to that rule would be graphing a line. If we had an mx plus b, then it'd just be as simple as like, all right, where's the y-intercept? Go from there using the slope, all right? But when it comes to something a little more complex, like a curve, like a parabola, like we're going to deal with in this chapter, okay, this will be the most information that we're going to need, and we're going to need to have an XY table to graph those points. Now, as with any XY table that we're going to be using to graph functions, I could chuck as many X values into that equation as I could please. And as I do that, what I'm essentially creating are coordinate points that I can graph visually onto a coordinate grid. And if I create enough coordinate points, I get the shape of my graph. But one thing mathematicians search for is limiting that work, making it more efficient. And one question they ask when it comes to graphing a parabola, a U shape, one thing a mathematician is going to care about is like, what's the fewest number of points I would need to graph a U shape? All right. Now, again, if I chuck enough x's into my XY table, I will get the full curve of my U shape, whether it's happy face or sad face. This is a happy face version. But again, what a mathematician is going to care about is like, all right, well, what's the minimum number of points I can get away with and still get the U shape? If I were to graph a single point, we'll call it the most critical point, the vertex. If I were to graph a single point of a parabola, that's not enough information because that doesn't tell me anything about the curve going up and away from it. It just simply locates its position. So 1 point's not enough. Even 2 points isn't enough because if I just gave you 2 points, that doesn't tell me enough information about like, okay, well, I can connect a line with 2 points, but it doesn't tell me enough about the curve. Because what if I gave you the 2 points like up here? That's not nearly enough information. So what mathematicians find is like, well, if I can get 3 points, namely, if I can get the vertex, if I can identify the vertex of a parabola and then pick a point on either side of that parabola, because this is what's called a symmetrical shape. Symmetrical shape means that this part of the curve right here is going to match this part of the curve right here, perfectly reflected over the axis of symmetry that goes down the middle. That's part of what we discovered and explored in the previous section. We worked on identifying like, okay, well, where is this axis of symmetry, this line that chops the U shape in half, and then in turn, where is this vertex? And then we picked a point on either side of the U. But here's the nice convenient thing about this section. We're going to be able to identify the vertex just by looking at the formula. And if we can identify the vertex, then I only need to identify a point to the left and a point to the right of that so that I can get this U shape. Now, it's not quite as random as picking like some point over here and some point way up here. There's a reason why we want to just pick a point equally distant to either side. And the reason is because this will be perfectly symmetrical. In other words, if I go through the work of finding the coordinate value here, I know that's going to have a corresponding point perfectly reflected over here. In other words, I don't have to go through the work on this one again. I can just solve for that coordinate point, and then I know it's perfectly reflected. And now, basically, given that point, doing the work for a single coordinate point, and then just graphing the side opposite, I have my U shape. That's the value of this section. All right. So let's jump back to the notes really quick. Because something I want to point out about this form, right? So this is the form that we're going to see. This is what's called vertex form. It's called that because this HK combination is going to represent the vertex. Now, the trickiest part about this section, and there's not much tricky about this, but the trickiest part is going to be in interpreting these values. So if you need to in your margins, make this note. H is going to represent the X value of my vertex. H is going to be, that X value is going to be what's inside the parentheses with the X in this form. But you're going to take the opposite value of what H is. I'll explain why in a second. You're going to take the opposite value of H. And what I mean by that is that if this said X minus 4, then H equals positive 4. If this said X plus 7, H would be negative 7. Again, I'll talk about why in a second. And then out here, K, or the Y value in your vertex, is going to be whatever sign is given out here, right? So if it said plus 5, then K is plus 5. If it said minus 3, then K is minus 3, right? And the reason why I take the opposite sign in here, but the same sign out here, has to do with this negative here and that positive there. The plus sign, the positive here, means I'm going to keep whatever sign K is, right? Whether it's positive or negative, I'm just going to keep K as whatever sign it is. H, that minus sign there, means I'm going to flip the sign of whatever H is. Okay, and the reason I take the opposite sign of whatever's inside the parentheses is this. I'm looking for when this parentheses goes to 0. I'm looking for when this parentheses goes to 0. And in order to do that, I'm going to take the opposite sign of what H is. So describing it maybe does not give you enough of a description. So let's just go ahead and jump right into an example so we can see it worked out. So what will you see on the section assignment? What will you see on a test? So our first example, first of two examples today, we're given this quadratic function in vertex form. G of x equals 1/2 times x minus 4 quantity squared. All right, a couple things to point out. First off, this is definitely a quadratic. It's going to result in a U shape, a parabola, because I have this x squared. Even though the x is in a parentheses, if I were to actually distribute and collect like terms here, I'm going to end up with an x squared. So it's going to have that parabolic shape, that U shape. The next thing to point out is this, just from a shape standpoint, A, this value out in front, still affects the whole parabola shape, just like it has in sections 1 through 3. A is going to affect the shape in two ways. The steepness, depending on how big A is. The bigger A is, the more steep or narrow that parabola gets. The closer to 0, like this number, 1/2, is pretty close to 0, right? The closer to 0 it gets, the wider or the shallower it gets, okay? And so the steepness is affected by the A value out in front. The second way it affects the shape has to do with whether or not it's happy face or sad face. And that purely has to do with whether or not this number is positive or negative. This is a positive 1/2, meaning it's going to be a happy face. Had it been negative, it would have been sad face. But that in this case, it's positive, happy face. That means it's going to open upwards. So just from like a reference standpoint, I know that this is positive. So I know I'm going to end up with the happy face parabola. And the fact that it's close to 0, that's a 1/2, I know I'm going to end up with a slightly wider type of parabolic shape. So I know that ultimately, when I graph it, it should look roughly like that. And then just identifying that location will be what I'm tasked with actually graphing it. All right, so I know generally what it's going to look like shape-wise, but now I need to identify where it goes. All right, so I need to create this XY table ultimately. So identifying the vertex will be handy, particularly since it's in vertex form. How do I know it's in vertex form? Again, since we're in the vertex form section, all of them will pretty much be in vertex form. But again, the dead giveaway here is the fact that I have this parentheses squared. This will be the signature look of a vertex form. All right. So using our knowledge from what we did at the beginning of these notes, in order to identify the vertex, I'm going to need to know what H and K are. Now you may be wondering, like, wait, there was no other value out here. What would K be? Well, technically there is a number there. We just don't bother writing it. The number that's technically there is +0. We don't bother writing it because anything +0 is just itself. But still, when I'm trying to pull this information out for my vertex, I'm going to need to know what value that is. It just happens to be 0. Okay. On the inside of the parentheses, there is a value there. And that value is this -4. And again, here's where, again, I want to emphasize. My H value here is going to be the opposite of this sign. So this -4 is going to become +4 for my vertex. So one of the first things you're going to be asked to identify throughout this section assignment is they'll give you a vertex form of an equation, and they're going to be like, all right, identify the vertex. What is a vertex? The vertex is a coordinate point, an XY combination, that you need to pull out the XY coordinate for that vertex. Okay, and that XY coordinate are going to be the H and K. Well, K is the more straightforward value here, so that 0 is what will go here. All right, the Y value for my vertex. The X value for my vertex, again, this is the trickiest one, so just make sure you have this written in your margins or off to the side somewhere. That I'm going to take the opposite sign of what's in here. Because if you recall, the form of the equation was X minus H. And so since this is minus as it is, the H is actually just going to be the 4. So it's a +4 for my X value. Okay, and here's why. Because if I were to take this 4 for my X value and plug it back in for X, let's see what happens. If I plug 4 in for X and I had 4 minus 4, I end up with 0 inside here. That's ultimately what we're looking for. That's considered a critical point when this parentheses goes to 0. So when I plug 4 in for X and this goes to 0, that 0 squared, or 0 times 0, also becomes 0. And I take that 0 and multiply it by this 1/2, that stays 0. And then again, technically there's nothing here, but if I were to add 0 to 0, shocker, I get 0. So from an XY table standpoint, if I were to take the 4 and plug it back in, I get 0 as a result. So this is definitely a coordinate point on the graph, but more importantly, it's the vertex of this graph. And so now if I were to graph this point, I have my critical point. The fact that it's a happy face, this is going to be the minimum value, or the base of that bowl, or that U shape that I'm going to have for my parabola. Now I can pick a point on either side of that coordinate point, and I can figure out the actual shape. So let's do that part next. Identifying the vertex, especially when you get practice with this will be the fast part. You're just looking for that HK combination. That literally is going to be your vertex. Opposite sign of inside the parentheses, same sign of the outside. Okay, there's my vertex. So how do I use that beyond just putting it onto a coordinate grid? All right, so I'm going to use this vertex. Now, again, I want to create an XY table. I don't need a ton of values here, but here's my XY table, xg of x, right? Now, I need 3 values in order to create this U shape. I want that vertex point in the middle, and then I want to pick a point on either side of it. So this 4, 0 is going to represent my vertex. All right, that's locked in. And there's the convenient thing. I don't need to do any math here. I could, on the solution sheet that I've uploaded to Google Classroom, that I'll show you in a minute, I go through actually plugging this 4 value in and spitting out this, this 0 value. So it is confirmed. It is, in fact, a coordinate point. It does work. But again, just pulling it out of the HK, I was able to get that coordinate point. Now what I can do is I can pick a value less or to the left visually from this point, and then a value to the right visually from this point, or bigger than. So you can literally pick any value you want, but again, you want to pick something that's symmetrical, so it reduces your work. So if I pick a value less than or left of this point, I could pick a number like 3. Okay, if I pick a number bigger than or to the right visually of this point, that would be like a number 5. But again, I did this on purpose. I could pick any number less that I want, like -80. I could pick any number bigger that I want, like 4.25, as small as it may be, it's still bigger. But again, I like to choose things that are symmetrical on either side, because then what that means is because it's a symmetrical U, their results on the coordinate grid should match. Because it's a perfect U shape, whatever value I get on the opposite end of plugging this into my formula, this should also have the same value. Because graphically, as I graph this U shape, if 4, 0, if it was right there, if this was my vertex, and I picked some value over here, right, on my coordinate grid, then it should, because it's perfectly symmetrical through that mirror, it should be perfectly reflected to the other side. And that Y value should match here, okay? That may have been abstract, so let me just go ahead and show you mathematically. So if I were to take this 3 value in my XY table and plug it into my function, here's my function, 1/2 times x minus 4 quantity squared. But instead of x, I'm going to replace it with that 3. Let's see what happens. So just from like a reference standpoint, really all you need to be careful at this point is order of operations. There's a lot going on in here, so just fall back in your order of operations. The first step of order of operations is parentheses. There is definitely something to do here. So if I do 3 minus 4, right? 3 minus 4, I'm going to get -1, right? So 3 minus 4, I got -1. All right, well, now after parentheses, I have exponent, so I have to do this -1 squared. Well, -1 squared is the same thing as -1 times -1, or the negatives will cancel, and I'll end up with +1. Right? I guess didn't need to entirely do that, but yeah, sure. So now I have multiplication last, 1/2 times 1, and this is going to give me a 1/2 result. And so I've created a coordinate point, right? I'm just making a mess on my board right now. I've created a coordinate point, right? So when I plug 3 into this equation, it spat out 1/2. All right. Now, I could go through the math here, but again, knowing that this is symmetrical, I know I should get the same exact value for this. Now, again, just for the sake of doing the math, I'll go ahead and go through the process again so you can see it done, the order of operations, but I should get 1/2 here as well. Okay, so let's confirm that. So the equation is 1/2 times x minus 4 quantity squared, but instead of that x, I'm plugging in this 5 value, right? And so when I plug in this 5, parentheses comes first, so 5 minus 4 gives me +1. So on the inside of my parentheses, okay, I'm going to get a +1. You may recall that when we did it up here, we got a -1, but what's going to end up happening is that this squared is going to make it positive no matter what. So when I square +1, or 1 times 1, I'm going to get 1 again. And then if I were to do multiplication last, 1/2 times 1, we end up getting what we should have from the very beginning. Again, a matched result here of 1/2. And what we've created are 3 coordinate points that if I graph this on a coordinate grid, okay, let me jump to the solution so you can see that done. If I were to jump over to this coordinate grid, right, here's the picture. I show all the work here. I go kind of above and beyond in showing the work, but it's good to see that every once in a while to see how the order of operations works. But focusing on the graph here, 4, 0, to the right, 4, up and down 0. There's the vertex of my parabola. And when I pick the point to either side, okay, there's the 3 that I plugged in and it spat out 1/2. So I went over 3 and up 1/2. There's the 5 value that I plugged in, went over 5 and then up 1/2. You'll notice that they are perfectly reflected over the axis of symmetry that goes through this parabola. And there is my happy face, slightly wider parabola. Okay. All right. So let's work through a little bit faster on our second example so you can kind of see this more in real time of what you would be doing. All right. So our second example today gave us this function. F of x equals -2 times the quantity x plus 2 squared plus 3. You were asked to graph this. So I need an XY table, right? So as far as work goes, I would immediately create my XY table. And I need to come up with 3 values so that I can graph my U shape. But I want the most critical value, my vertex of this parabola. From a shape standpoint, because it's negative for my A value out in front, because it's negative, I know it's going to be sad face. The 2 tells me it's going to be slightly more narrow than a regular parabola, right? And then my H and my K are going to give me the actual vertex location. So when it comes to identifying this vertex, that'll be the first thing you're going to be asked to do in these problems on your assignment, which again is a coordinate point. H, take the opposite sign of what's inside the parentheses, because again, I want the parentheses to go to 0. But the opposite sign here, the opposite of +2, would give me a -2. Outside the parentheses, this is K. The K is going to tell me, again, I want to take the same sign as the K, so the fact that it's a +3 leaves it at +3. Now I have my vertex. Graphically, I would go left 2, up 3. That locates the critical point here. Because it's sad face, that's going to tell me that this is going to be a maximum point. And so in my XY table, I can just throw down my vertex. No need to do any calculation there. I could take this -2, plug it into this equation, and I should get a +3 result. Here's why, just really quickly. If I were to plug -2 in here, -2 plus 2 is 0. 0 squared is still 0. That 0 times -2 is 0. Basically, all that goes away, and then look what I'm left with, +3. There. So anyway, but that was confirmed anyway. There's my H and K. I could have just done that. So now on my XY table, I just pick a value less than -2 or a value left graphically, like say -3, and a value greater than or to the right visually, right? So that'd be like -1. I could plug these back into my original equation. This one's obviously a little bit busier. Just be careful with order of operations. So I'll do this one. -2 times the quantity x plus 2 squared plus 3. And I'm going to replace that x value with that -3. Let's see what happens. And I know automatically whatever result I get here, because it's symmetrical, it's distance away from the -2 here, that this value will end up matching whatever I get here as long as I do it correctly. So if I plug in the -3, I have to do parentheses first. -3 plus 2 gives me a -1. I erase this as I go, but feel free to take as much space as you need on your scratch paper. Okay, so now I would do exponent. -1 squared, we've dealt with this before. -1 squared is the same thing as -1 times -1. The negatives will cancel, and I'm left with +1. Okay, now multiplication comes next. The -2 times +1 will give me -2. And now I do addition last. -2 plus 3 is going to give me a +1 result. And again, here's the nice convenient thing. Because this is symmetrical, this result has to be perfectly matched here. There are my 3 coordinate points. And if I go to my coordinate grid on my solution sheet, just to kind of see the result here, right? So this was that problem. There is the -2, 3 vertex, left 2, up 3. Picking a point left and right of that, these 2 little green dots here represent those. There's the -3, +1 result we got. And then when I know it's perfectly symmetrical and mapped to the other side, there's the -1, also +1 result. Okay, I show the work for all 3, but there would give me my U shape. Again, because it was a negative out in front, there's my sad face U. And because it was a 2, it's slightly more narrow than what a normal x-squared graph would be. And that's how you would graph using vertex form. All right, let me go ahead and stop recording.